Alright, welcome to another video on fluid mechanics, and what we're going to do now is we're going to look at another example of viscosity and shear stress in fluids, where we're going to look at a particular problem that is relevant to mechanical engineering. So basically we have a shaft that is rotating at a speed of 500 RPM, and the idea is that we are going to have basically just a layer of lubricating oil surrounding that cylinder. So you can imagine that the shaft is basically just floating in this fluid here, like we have here in the cross section, and then there's a hollow cylinder within which that shaft is contained. Now the actual lubricating oil in this case has a viscosity of 0.9 newton seconds per meter squared, and we're given the dimensions of the shaft and the outer cylinder. So using the basic principles we have learned so far of viscosity and shear stress on fluids, we should be able to calculate the total torque required to actually rotate that shaft at this speed of 500 RPM. So the starting point is basically noticing that the gap here is going to be considerably small, so we can approximate the velocity profile of the fluid as a linear equation. So we have our depth here, y, from the outer cylinder to the inner shaft. And you notice that we can perform this approximation just in the same way that we did it in the last video. Now the tricky part here is noticing, okay, so how do we find the actual velocity here? Well, the velocity is going to be related to the rotational speed. So what we can do is we can basically write down the equation V is going to be equal to angular velocity times r, or basically in this case it's just the angular speed because we're talking about just a two-dimensional case. And obviously if we want to express the velocity or the speed in terms of meters per second, we're going to have to convert this first. So omega, if we wanted to convert it into, so let's say this is radians per second, then we would have to take this original velocity, but we would multiply it by 2 pi on 60. And then we would have RPM here. Alright, so that's the first step here. So basically we can write this, we can write the following. V is going to be equal to 2 pi on 60 times omega, as is given here. And then the radius is just going to be the radius of this shaft, which is going to be half of this. So that's going to be 0.05 meters. So now we put those values in here. This is going to be omega is just 500, 0.05, and then put this in the calculator, and that should come down to 2.618, so 2.618 meters per second. Okay, so that gives us the maximum velocity here, and you might be thinking, well, how do we know that the velocity profile is going to be at a maximum here? Why not here? Well, the shaft, in this case, the shaft is the one object that is moving, so it makes sense that the fluid is going to become displaced here before it becomes displaced at the top. So the layers of fluid are going to be moving faster here because that's going to be relative to the motion of the shaft here. And that's why the profile looks like this. So this is going to give us the velocity right here at this point of the contact between the shaft and the fluid. And the distance y, or the thickness of fluid, we can calculate it from these two quantities. So basically we have diameter 2 minus diameter 1. And we're going to divide that by 2 because if we take the difference, we're going to have two depths here. We only care about one. We're taking about the thickness around that ring. So we're going to have 0.15 minus 0.1 over 2. And that's going to come down to 0.025 meters. Okay, so now the next step is, well, we know what the thickness is, we know what the height of that velocity profile is, and we know what the velocity is at the maximum, so we can calculate the velocity gradient. So that's going to be dv over dy. So the velocity is just going to be 2.618. And the depth is just going to be 0.025. So let's see what that gives us. That's going to be equal to 104.72 meters squared per second, I believe. Oh no, actually, it's going to be the following. So it's going to be just seconds to the power of -1, because the meters are going to cancel out from this division. Okay, so that's the velocity gradient. And now with that, we can actually calculate the shear stress of the fluid. So that's going to be equal to the viscosity times the velocity gradient. So this is going to be equal to 0.9, which is the value that we're given in the beginning, times this. And that's going to come down to 94.25 pascals of shear stress. Now we're asked to find the torque. So in order to do that, we need to find, first of all, we know that torque is just force times distance. So let's call that distance d. And this force is going to be related to the shear force. So the shear force is going to be shear stress times area of contact. Now area of contact is important because it's not the cross-sectional area, but rather the area that is actually in contact with the fluid. In this case, the area is just the area of the wall of this cylindrical shape. So in order to calculate that, we're given the length, which is 30 centimeters, and we know what the circumference is because we can calculate that from the diameter. So in this case, the area of contact is going to be the circumference, which is just pi times d1. That's the diameter of the shaft. And we're going to times that by the length. So let's see what that gives us. We're going to have pi times 0.1. And then the total length of the shaft is 0.3 meters if we convert it. And this is going to be equal to 0.03 pi. I'm just going to leave the pi there just to make it more accurate. So this is going to be in meters squared. Okay, so now we know what that is. We know what the shear stress is, so we can calculate the shear force. So this is going to be 94.25 times the area. And let's see what that gives us approximately. That's going to be 8.88 newtons of force. And now the actual torque is just going to be this times, well, the distance from the center of rotation. So that's just going to be the radius of the shaft. So we're going to have d1, which is the diameter of the shaft, over 2. So 8.88 times 0.1 over 2. And that's going to come down to 0.444 newtons meters. And that's going to be our final answer. So based simply on the material property, in this case the viscosity of the fluid, and just the dimensions of the problem, we were able to calculate the total torque that would be required, or at least the minimum torque, to achieve a rotational speed of 500 RPM. So hopefully you can see that using shear stress and viscosity can be quite useful for solving these types of problems where you have fluid motion with respect to a rigid body.